Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Python hacks, and in these tutorials I'll be explaining you guys some different interesting and topics related to Python and relevant programming languages which can be coupled with Python. Okay, in today's tutorial I'll be explaining you guys about an interesting concept, not actually a concept but more of an interesting module available in Python called as Numba. Okay, now for those of you guys who want to know what exactly Numba is, who doesn't know, haven't heard about it, okay, go to this website, go to this web page. Um, Hold on. Okay, go to this web page called as number.pydata.org, and this page will look something like this as on today. Okay, but it might be slightly bit different and you can read through about it. Okay, and these are for the full details, and also if you just click the documentation and user manual, you'll have an extremely well defined documentation over here which you can just scroll through and read. Okay, for some simple explanation as to what this is and everything, I'll just open up my slideshow today and I'll explain you guys what's happening. Okay, now in this tutorial we'll be looking at Numba, and we'll be using that as an example. As an example, we'll be solving the linear advection equation using Rangikutta fourth order method using Numba and in comparison with Python to see how things go by. Okay. Now in this video I'll be explaining you guys about Numba, the difference between a compiler and interpreter, how Numba behaves something like a trade-off, and I'm going to show you guys this code example, and I'm going to say about some of the features that are available in Numba that you can go through. Keep in mind this is just an extremely simple this is going to be a simple explanation of only one feature in Numba, but other features can be implemented so easily, so it's not that difficult. So if you just understand one of the features, mastering the other feature is quite simple, so it's not a problem. Okay, now what is Numba? Numba is actually a module that enhances the NumPy operations quite nicely. Now what it does is actually the second point. It produces optimized machine instructions for Python functions. Okay, now to understand what this means, okay, you'll have to go through about how the compiler works and the interpreter works. Okay, so hold on that thought for a moment. I'll explain you guys in a moment sometime. And Numba uses LLVM compiler infrastructure. Okay, LLVM stands for low level virtual machine compiler for producing the machine instructions. Okay, and Numba has several classes, decorators like JIT for doing a lot of operations and stuff. Okay, now as I told you guys, I just told that Numba produces optimized machine instructions for Python functions. Okay, now what does this mean? Now before we understand this, we need to know about a little bit about compilers and interpreters. Many of you guys will know what a compiler is and an interpreter is. For those of you guys who do not know much about it, let me guys give you a small brief overview. Okay, compilers and interpreters are two kinds of program reading software that processes your source code and makes machine instructions to your computer. For instance, computers understand only zeros and ones, binary values. Okay, so if you want to do any operation, you just have to write them in machine level code, which is in zeros and ones, or assembly level code, which is kind of similar. Okay, I'm just using the words very loosely, so don't take it too literally or pedantically. Okay, because I'm not an expert in this field, so take my words lightly here, but get the overall point. That's more important. Okay, compilers and interpreters are some software that helps to generate machine level instructions based on your program codes. Now your computer will ultimately understand only machine level language, which is made from binary values in zeros and ones. Writing a program in that will be extremely difficult and complicated, Okay, and we need a higher level of programming language, and that's why we use high level programming languages like C, Fortran, Python, Java, and several others to do our option. And now what compiler and interpreter does is that I mean the high level languages like C, Fortran, or Python, or MATLAB, or whatever, okay, and produces some machine level instructions to do the job. And that's what compilers and interpreters do in general. Okay, now but the way in which compilers and interpreters work is differentiated very severely. Okay, in compilers, this is how the compilers work. In compilers, all the codes, if you write like a one big file, let's say one big C program, or a one big Fortran program, or C++ program, whatever it is, the compiler will just go through all the lines of code in that in that program and checks for errors. If there's no errors, then no problem. Then once all of them are read, it creates memory allocation instructions and machine codes, create machine codes for each and every line, and then each and every line. Okay, and this machine level instructions are in machine level language, are some instruction which ultimately get translated to zeros and ones. So these, okay, and these codes are actually checked to see if they are working fine, and the unnecessary codes, the unnecessary and redundant codes which get generated in these processes are removed. What I mean is, if for each and every line some machine level instructions and codes will be generated, and it will be compared with the machine level codes generated for the program codes above and below and everywhere, and then based on all the values, some unnecessary codes are just chopped off, and only the most essential and fundamental codes are retained. Codes are retained, and as a consequence, this code will be proper, optimized. Memory wise, it will be efficient, and also it works faster. That's why this software is actually called as a compiler, because it does not literally translate all the main instructions into codes. It just goes through everything and gives you guys a list of machine codes, which is a summary of all the instructions to be done by you. Okay, it kind of gives you a compiled picture of what's happening. That's why it's a compiler. Okay. Now, after this optimized machine code is made, they are saved in object files, and then the object files are linked together to produce an executable file, like an exe file. Okay, and this executable file then takes in all the data when executed, and takes in all the data and does all the instructions that you've told, and then produces and does all the operations you say. And that's how compilers work. And some of the programming languages that are compiled uses compilers are actually C, Fortran, C++, and many more. There are many more. Whereas interpreters, they work in an entirely different way. What interpreter does is that if you have a set of instructions written in say a Python file or something, each and every line is read one by one. Okay, so for instance, the first line is taken. The compiler reads the first line, and then it interprets the line into an equivalent machine code. Interprets each and every code into a machine code. So memory allocations and instructions are made for each and every line it reads. Okay, first it reads line 1, creates machine codes and memory allocations for that line 1, and then that code is executed immediately and does a part of the entire all the instructions, does some work. Okay, does some work, and then that line is taken off. That line goes away. Okay, goes away, and then the second line is read. The machine codes are generated, does some job. The third line is read. Machine codes are made, does some job, and this entire cycle of steps 1, 2, and 3 gets repeated again and again and again for each and every line till all the lines in the source code are read and completed. Completed. This kind of an architecture is implemented in programming languages like Python, R, MATLAB, and several others. see, there are advantages and disadvantages of using compilers and interpreters. Okay, the as far as if speed is concerned, compilers are the fastest because the compiled code, which compiled machine code, is highly optimized, which has it's very sharp, to the point. It cuts the chase and goes to the point, and it does the job properly. Whereas an interpreter, the codes are generated for each and every line, and they are deleted, and then a new set of machine codes are generated for each and every line, and these machine codes are not compared with the machine codes generated for the previous lines and the next lines. So as a consequence, they tend to be slower. Okay, they tend to be slower, and occupy a lot of memory, and then gets removed. So you have a lot of memory fluctuations here for interpreter. But the advantage is that despite being slow, interpreters are helpful to generate do a lot of functions one after the other. Whereas in compiler, a single line cannot do a certain option. Single line cannot be executed. So a program has to be made which has to merge all the instructions to be executed in a single shot. Whereas interpreter, each and every line can be executed separate, one independently of each other. So these are the things and advantages and disadvantages of interpreter and compilers. Now, Numba is actually kind of like a trade-off. Now, what it does is as follows: if you write a Python file, okay, and in the Python function definitions, on the function definitions, if the function definitions have a decorator defined before it, then the entire function is marked for compilation by Numba, okay, by the Numba decorators. And then here's the thing: when the interpreter interprets one, just goes one line after the other through the entire program, and whenever it meets the above functions marked by Numba, then Numba makes the interpreter to read the entire function. Instead of every single line of the function, it tells the compiler to read the entire function. And then this Numba, with the help of LLVM architect infrastructure, it generates machine codes for these functions. Okay, and these machine codes are compiled. As a consequence, you get a compiled machine code for these functions instead of an interpreted machine code. Okay, for the function, you get a compiled machine code for this function. Okay, and that function is machine instruction is kept as it is whenever the function is invoked, or if it's cached, and if it's not, it just gets generated on the spot when it's needed, like that. And then whenever the function is invoked, these compiled machine codes are called to do the job. So whenever the Python interpreter comes across these functions, what it will do is that it will not go and interpret the machine codes immediately. Instead, you just call these compiled machine codes which are made for this function, and when those machine codes does the job, and everywhere else the interpreter does its routine job of translating its code one after the other. So as a consequence, what we have is that we have some features of some parts of the program, okay, where your interpreter kind of behaves like a compiler during the execution, and as a consequence, you have some compiled machine code present, being generated during the generation of interpreted machine code. So this is kind of like a trade-off. Number kind of forces Number kind of forces your Python interpreter to behave like a compiler for a short period of time. Okay, using the features available in LLVM, and if without LLVM, this is not possible. And what the thing to be kept in mind is the compiled machine codes tend to be more optimized when compared to the interpreted machine code. So that's the thing. Okay, as far as the features in Numba are concerned, there are like several features like JIT. JIT is the one we are going to see now, and this stands for just-in-time compilation, and this is this is what it does. And then there are options to cache the machine level cache these machine instructions and keep them separate. And then there's this code for vectorization, okay, which will be useful for vectorizing functions in Python in Number. And if you guys want more details about what are the other options available and everything, you can just go to this link, and this link is working as on 2nd January 2016. 2nd January 2016, so it might be varying after some time, but anyway, if you guys want to figure out where this is, just type Numba documentation in Google and you'll get it. Okay, and if I go to this link over here, okay, this is actually my number.pydata.org, my homepage, and this is the documentation. So if I click this is the documentation. I will if I click this, there are like several documentation links available. So this is the latest version, I guess. And if I click this, I'll get the index, and then I'll get the index, and in this index this is the first one is the user manual, reference manual, and a number for CUDA GPU and everything. And if you just go to the user manual, you can just check all the options like overview, how to get started with it, how to use JIT, how to specify some compilation options like no Python, no GIL, cache, and everything. Okay, there are options for creating universal functions using vectorize, decorator, and GU vectorize, decorator, and several others. Okay, and you can also run parallel programming kind of stuff, like which is multi-threaded options using Numba. And Numba also has certain features to make the programs run in the GPU or the graphical processing unit using CUDA. Like if you CUDA is actually a kind of programming language for NVIDIA processors, I guess, but which uses C or which has its own version of C, C++, or Fortran to do the options. And now what it does is that using CUDA you can make the graphical processing unit or your graphic card in your system to do the operations. So what it does is that your host, which is actually your CPU, will take care of the option, whereas your GPU, where some of the parts of your execution goes to the GPU. Okay, and goes to the GPU and to do some operations. And if you guys, and mostly CUDA language that you get supported uses CUDA C for Numba, and that is offered by NVIDIA. So if you guys want to know if you guys are good in CUDA C or C programming, then you have a guide over here which you can just go and have a look at it. And you guys, and you guys can read this if you want. They just explain how good the programming options, how good the floating point operations increase and everything. So this is kind of really interesting stuff. These are like highly advanced stuff, but kind of interesting to look at least. These are very useful. Many people use it. For some simple applications, this may not be needed. For some real-time hardcore works, some of these operations will be really useful. So it's good to have a look at it once to see whether whether it suits your guys' need or not. Okay, with that I'm shut. With that, this is over, and now finally let me go to the code. Boy, this explanation is long, so I'll just make the code simple. And now what I'll do is that I'll just explain the program. I'm going to use linear I'm going to solve the linear advection equation using Runge-Kutta fourth order schemes. Okay, and now if you guys do not know how Runge-Kutta fourth order scheme works, you guys have to check this out on the internet. it's actually a highly optimized numerical method scheme, which helps to uh, which helps to do it helps to time match and find solutions to equations which do not have a proper analytical solution, okay, in a numerical manner, okay, uh, in a numerical manner. Okay, now this is the thing. Now what these are the function definitions which I've defined on the top. Let's not go to that immediately. I'll go to the thing. See, what I have here is as follows. For my function, okay, for my program, what I have here is that I just have excuse my poor drawing skills. Okay, now what I have here is that I just have a region, a straight line region whose length is about 1000 meters, and what I have is that some kind of a value, say u, which is sinusoidally distributed along this length. Okay, and now this is the value u, and it varies with x and time. Okay, and okay, I think that doesn't look like a t. Okay, and this is your x. Okay, this is your x, and now this value u can be anything like temperature, or how do I put it? It can be like temperature or some humidity, or whichever, whatever value you keep it. It's not velocity, but some other value. Okay, and this thing is actually moving towards towards my right with a velocity of 2 meter per second. Okay, so by 500, and this is actually a time instant t equals 0 seconds. Okay, now what I'm going to do is that I want to see how this temperature wave or the humidity wave travels in for every time step, for every time snap from t equals 0 to 1000 seconds. You just want to see how this wave moves from here from 0 to 1000 seconds. And what I'm going to do is that what I also did is that during my program, in this program, for every time step, for calculating the value for every time instant, this value over here, the last point, okay, will be copied to the first point for every time of the next time step, meaning the last point of time t equals 0 will become the first point of time t equals 1 over here, and thereby what will happen is that you'll have a continuously moving sine function throughout the regime, throughout this 1000 meter regime. Okay, and I'm going to have 1001, okay, not 10,000. I'm going to have 1000 points. So this means I'll have like 1000 intervals. Okay, space is 1000 spatial intervals. Okay, and I'm going to have about okay, let me just check this out. I'm not sure. Where is it? Okay, fine. And then where is it? Yeah, and then I'm going to have 4001 time steps. So you'll have like 4000 time intervals. So you'll have like 4000 time intervals. So you'll have like you're measuring how the wave moves for every 0.25 seconds. Okay, and the distance between 2 points is actually 1 meter. Okay, this is the logic I'm going to do. And in my program, I define the time steps to be 4001 seconds, number of spatial points to be 1001. So initially I'm defining this u value, which is actually the temperature or the humidity, to be anything. So I'm just defining them to be 0, and it has all okay, and this is actually the length. I'm setting the velocity of this wave to be 2 meter per second, the length of the entire regime to be 1000 meters, getting the value of pi to this value pi, and then getting the value of, I'm setting the total time to be to analyze this as 1000 seconds, and then using the above logic which I explained in the illustration, I'm going to have the space steps and time steps defined over here, and I'm going to calculate the CFL over here. CFL is actually a criteria to see whether your numerical code will be stable or not. For these code, if the numeric CFL is 0.5 or less, the code will be stable, and if it's little more, I guess the code might turn unstable. And then what I'm going to do is that I'm going to I've imported numpy on the top with the name np, okay, and I linearly defining 1001 points between 0 and L, and using x, I'm defining u to the first time instant u of 0 to be to have the sine function, okay. So this will range between 0 and 1 and -1 to 1. So if I want, I can set this to something like 20 times that, so that I'll get a temperature distribution of between +20 and -20 thing. But anyway, this doesn't matter. This is just an arbitrary value, okay. And then this is what I'm going to do using the time function available in the time module. Okay, I'm setting start1 to be time. Okay, what it does, this function does is that it just calculates how much time has elapsed from some reference point in the past till this point where the function is clocked in. Okay, so it's going to give me some time snap. Okay, it's going to give me a time snap. Okay, and then this function gets called. Okay, and this is actually the Rangikuta function, which I'll explain in a moment. And then this line is called, and when this line is called, it's going to give me another time snap. So if I subtract these two, it will give me in seconds, like how much time it took for this function to execute completely. Okay, execute completely. And I'm going to get a print statement like normal RK4 process took this much seconds to do the option. Simple as that. Okay. And then what I'm going to do, I'm just resetting the values of x, u, and everything. I'm resetting the values and everything. I'm doing the same process this time with rk4_2, which is actually the Numba rk4, the function which is which is operated by Numba. Okay. And now let's look at the function definition. Now what I have here, this is the normal function. The first one is actually the normal function which does the Rangikuta operations. Okay. Now, if you guys write the linear advection equation properly, you guys just write the linear advection equation properly, you guys will understand what's happening over here for Rangikuta scheme. Don't worry about it. These are just some operations. Just keep in mind that these are some arithmetic procedure done for the operation. Just take it as an illustration. This method I'm using for RK4 can be applied to any method. So this is just a symbolic way. So I'm just telling it symbolically. What I mean is, this is just some execution. Instead of this, you can do anything. It doesn't matter. The procedure is essentially the same. Okay, now what I'm doing is I'm doing all the four calculations for all the four levels of calculations we've done for RK4 in these lines, and this for loop with I as the iterator is for the crap. I think this is time step, right? I forgot. This is actually a time step. This is actually for the time step. I don't know how did I forget about it. Anyway, moving on. This is actually for the time step. Okay, this for loop with I as iterator is for the time step, where this part is for the spatial stepping, and this will calculate the total value using the RK4 methods and everything. Okay, and this is for reinitialize, this is for setting the last point of the previous time step as the first point of the current time step, this way. And this is how your RK4 function works. And what I have below is that exactly the same function but with the decorator. Now the decorator I'm using is JIT, and this JIT is actually imported from your module, your Numba module. So I just wrote Numba, from Numba import JIT, and once that is done, for this function I just write at JIT at the top, and that's it. Now if you write this, it's implied this is, you're telling to the you're telling to the Python compiler, you're telling to the Python program that okay, hey, guess what, this function below is decorated by me. Okay, so when you come across me for this entire function, keep that in mind. Okay, so when the Python interpreter just goes through this entire program one after the other, so whenever it come across this JIT, okay, it just takes the entire program, this entire function, and processes that, uses LLVM to produce an optimized compiled machine code, and that gets done. So what happens is that this one is RK4_2, which is actually the JIT based number RK4 function, whereas this one is just a regular RK4 function based on Python. So that's why you get two ones. Like normal RK4 process took, this is a normal RK4 function, and this is your Numba JIT RK4 function. So these two are different. These two may look exactly the same, but they'll have different machine level codes. This will produce an interpreted machine level code, whereas this is produce a kind of like a compiled machine level code. So difference, speed wise, there will be difference. So what I'm going to do is that I'm going to clear this terminal. I'm going to run this file. If I run it, okay, it should take some time, and hold on, this will take some time, and because there are like so many points to look at. There you go, you see the difference. The RK4 okay, let me just look at the code again just for clarification. Okay, fair enough, it's fair enough, it's working fine. See, the normal RK4 method took like 16 seconds to do the entire operation for this, whereas your number based JIT, your RK4 function took like 0.58 seconds. So if I want to run this again, you can check this out. This will take a while. Okay, so it's consistent, so it's taking like 16 seconds for the entire operation, whereas compiled RK4 takes like only 0.5 seconds, 0.6 seconds approximately to the entire option. Now if you see, you have like approximately 32 times speed up because of this code. And how good is that? Now the thing is, you might argue that, hey, if you were to vectorize this function, you can get a little more better option. Fair enough, I agree, and that's why I just mentioned that this is just a simple this is just an introductory video. In a complicated video, in a little more advanced options, you can do a lot more with that, so it's perfectly possible. And what I'm going to do is that this time I'm going to raise the stakes, and I'm going to make it much more complicated. This time what I'm going to do is that I'm going to make the time steps to be, I'm going to increase the time steps to be 8001. So I have like 8000 time steps, and I'm going to have like approximately 2000 space points, thereby making it even more messy, whereas the CFL will remain the same, okay, for this process. So if I were to run this, the CFL is the same, but will take me time. So I'm going to pause this video for a while so that I do. Okay, welcome back. So if you guys look at it, when I just increase the number of time steps by 2, and when I increase the number of space steps to be 2, Okay, when I do the same operation, it took me like approximately 62 seconds for the entire operation to be completed where by the normal Python function, whereas it just took me like 0.8 seconds to do the entire thing. Now the thing is, for to amp up to make this things even more serious, what I'm going to do, I'm just going to make this to 16,000 seconds with 4001 space points. Okay, 4001 space points. I'm going to run this again. Okay, now it will take time, so I'm going to pause this video and come back in a moment when this entire thing is done for you guys to get a good feel. Okay guys, welcome back. Now if you guys look at this, now this is phenomenal. Like this entire thing just took about it took about 46 something seconds using the regular RK4 program using regular Python. Okay, took like 246 seconds to do the option, whereas your Numba code takes only 1.65 seconds to do the entire option. Now if the thing I'm trying to make here is, just by adding one decorator to an otherwise Pythonic code, you're able to make such a tremendous leap. Now imagine, this is just a sample program, but imagine you have a very complicated program in the future which has about which has a lot of computation to do. Imagine the kind of time saving you'll get. Imagine the amount of time saving you'll get using Numba. Now that will be really phenomenal and useful. And now the thing is, if everything goes well, sometimes the functions might be even faster than might be really fast, that you may not need to use compiled programming languages like Fortran or C. Like in one of my previous tutorials, I would have explained that in some cases where the situation demands you to use compiled programming languages to take care of some heavy duty stuff, you have to use Python or C bindings or Fortran or Weave or some other option to merge C programs or Fortran programs into Python to get the speed number crunching done quickly. Okay, now this is an alternate thought. Instead of going with a compiled language, instead of going with multiple programming languages, this one is elegant, because you're literally just doing all the options with just one programming language. All you're doing is just making a small correction on the top within the same programming language, and that too not much of a thing. But this is more easy. Instead of writing the entire function into another programming language and translating it to some shared object file and then importing it as a Python module, this is kind of elegant and simple. Okay, now that's the power of Numba. Now I'm not sure about the future, but some people speculate that if some of the developments are done nicely in Numba, you might get some code which are extremely optimized, such that they are much faster than what you might get in Fortran or C. Now that will be remarkable. Now people say that these are just some days away from making it real, but that's a very good, very interesting thing to hear about. Okay, when that happens, this kind of tools will get real more benefit and advantage. Okay, now with that being said, and that's all I have for you guys in this more or less extremely long tutorial. Thank you guys for watching so patiently this one, because this concept is kind of goes really deep, so you need more explanation for this. Thank you guys for watching, and see you guys in the next tutorial. I'll just try to come up with some interesting tutorial another interesting tutorial next time. So see you guys, take care, and bye.